So, hello, good morning, buongiorno. Can everybody hear me? Can everybody? So, I have to apologize in advance if my voice sounds a little bit strange this morning. I speak too much, and this is God's way of punishing me. So, just let me know if the sound goes a bit funny. So, I'm going to start by asking a question. And the question is, how do you tell if a person is healthy? How do you know if a person is healthy? Do you measure individual cells? Do you check to see that the ion flow rates are at different levels? Or do you check emergent properties? Do you check the pulse and the temperature and the heart rate? And my proposition in this talk is that when we build microservice systems, we can't measure normal things like CPU and network flows and that sort of stuff. We need to measure the emergent properties of the systems, because when you build a system that has 100 or 200 moving parts, it has different properties. It's not the same as building systems where you have 10 web servers and one load balancer. In a microservice system, you might have 100 microservices, and they all speak to each other in different ways. So this talk is, it's not a description of how to build systems. So my company, Nearform, we started as a Node.js consultancy about 3 years ago. And if you use Node.js, you know that it is quite good at building microservices. So you go towards the microservice architecture naturally. And we've built about 50 plus systems for startups and for big companies. And we've learned a lot of stuff by doing lots of mistakes, building systems that didn't work, and lots of pain. So this is an empirical, it's an empirical report, a kind of a summary of some of the things that we've learned. And I think this space for microservices is something that is still in an area of discovery. I don't think anybody can tell you today, in 2015, this is how you build microservices. I think there is a lot of research. There's a lot of production systems that are giving us information, but there's a lot left to learn. And this is where we have come to. So I have to ask the question, who is using microservices in production? Put up your hand. So that is about maybe 5%. This is normal. I usually see 5 to 10% of the audience using microservices. It is an interesting question, what is a microservice? And if you look at a lot of the blog posts and some of the books that are coming out, a lot of people are using them in a limited context where they are essentially small web servers that talk over HTTP using JSON. I think that it is a small subset of what microservices actually are. And when I talk about them, I mean a much more general picture. I mean a system of communicating independent processes. And they might be communicating point-to-point with HTTP. They might be communicating over Redis, pub/sub. They might be communicating using a message bus. Or they might be communicating using WebSockets. Who knows? It doesn't really matter how you structure the communication. The mental model of microservices, the one that's powerful is that you have lots of independent pieces. And they talk to each other using messages. And this is the most important thing. It is not the services that are important. It's the messages. The message flows, the types of messages, the ways in which they flow through the system is the important thing. And that's because messages and message flow rates and how services talk to each other are independent of how services are configured and how services are deployed. So you see a lot of discussion of the issue of, let's say, service discovery. And you have solutions like Zookeeper and Console and things like that. But But in some ways, these are not the important problems. So, for example, if I have a system that is built using microservices and users can log into the system, during the day, 100 users per hour log in, and at night, 10 users per hour log in. That number, that rate of login is independent of the number of login microservices that I'm running. So I might run 5 independent login microservices to spread the load. But those 5 services and their CPU loads don't really correlate in a useful way to the number of logins. What counts is the number of logins that are happening at different times. If you track that figure, it lets you do interesting things, particularly when you start trying to use the power of microservices. So the real point of microservices is that I want to change my login microservice. I want to add new functionality. I want to be able to do that by taking those 5 services and one of them I upgrade. So 20% of my traffic is going through a slightly newer service. And I can see, does it break anything in production? And the login microservice is independent of the rest of the system that does the shopping cart or content delivery or any of that sort of stuff. This is the point of microservices, to be able to do these partial deployments. So let's say that I deploy a new version of my login service. And I'm measuring the rates of user logins, and I see this effect. So this chart is a made-up chart, obviously. And it's showing a rate of user login slowly declining. And then I do a partial deployment, and suddenly my rate of user login starts declining dramatically. This is a much more useful measure of the quality and the health of the system than any number of unit tests or acceptance tests or any of those other quality measures that I would have used normally in best practice software engineering. Because this is real data. This is real data in production. And in fact, the power comes from not taking a new version of login and just sticking it in production and throwing production traffic at it and allowing your system to break. The real power comes from splitting your production traffic and running it against the new service without actually harming your users. So if you split the traffic, send some of it to the new service and then throw away the results, but use one of the old ones to actually serve data or serve pages back to users, you can tell if the new service breaks on production. This is much more powerful than any amount of quality testing because this is real data on real traffic. And when you come to deploy things, no matter how much testing you do, production is always different. So it comes down to how do you measure microservices to get quality? And there are many ways of doing it. But the one that I'm talking about today is looking at a very simple metric, message flow rates, the number of messages of a certain type per minute, the number of login messages, the number of purchases, the number of clicks on a certain link, the number of emails that the system is generating. All of these message flow rates are useful metrics, and they're much more useful than traditional ones. They're much more useful than pinging a microservice every 30 seconds to see is it up. Because it might be up, but it might be malfunctioning. So if you take that basic assumption that message flow rates are going to give you useful information, the next question to ask is, how do I know what to measure? How do I know what to look for? And as part of our work building these microservice systems and focusing on the message patterns rather than the services, we've seen a simplified set of patterns that emerge in these architectures. So I'm going to discuss 4 of them. This is not complete, and maybe some of these patterns are too simplistic, but again, we're at the point in this microservice architecture where we are discovering what the actual patterns are. And these are the ones that we tend to use in practice, and these are the ones we tend to have found useful for measurement. Um, a simple and obvious one is an actor pattern, where you have a panel of microservices that act one at a time on different messages that come in. So image resizing, maybe, something like that. Another one is a subscriber pattern. And these have analogs in older style message queue systems. But the systems themselves, the individual units, are microservices. They're much smaller. And this might be used for something like generating special offers, depending on if a user logs in, you have different microservices that might generate different types of special offer. In this case, you can see that instead of one message, there's 6. Another pattern might be a chain. So if you are building an e-commerce system and someone checks out, there's a set of processes that have to be followed, an invoice has to be generated, an email has to be sent, different things have to happen in series. Another one might be a tree pattern, where an individual service generates a message that then generates further messages in different types of microservices. And the top of the tree, the root doesn't really know what the rest of the tree is going to look like. This is actually quite common. You may not design this pattern, but if you're using microservices aggressively, your system tends to end up looking like this over time. So again, I'm going to return to this question of why are we building systems that look more complex than traditional monolithic systems, where you build a system and you deploy it into WebLogic or IS or something like that, and it's a proper object-oriented system with inversion of control and proper dependency injection and proper object-oriented structures and all that sort of stuff. The real reason that we do this is to deal with risk. So the problem with monolithic systems is these big bang deployments, where you do a release every quarter. And it's hugely stressful. And you do a big data migration, and you deploy a new version of your system, and then it goes horribly wrong. One of the most famous examples is a high-frequency trading company in the US, a company called Knight Capital. And if you look for them on Google, they lost something like $450 million in the space of 45 minutes because of a failed deployment. Right? So they were running 8 servers, and they deployed 7 correctly. And the last one, the 8th one, had the old configuration and the new system. And they just started buying all the shares. And even though the guys running that system within 5 minutes realized that something was wrong, they started undeploying. So they ended up with 8 servers with the wrong configuration. So they had 8 servers doing the wrong thing. In fact, if you read the Securities and Exchange Commission, which usually does financial reports, they actually have a technical report on the deployment failings of that company. So the whole point about microservices is to reduce that risk, and the risk is reduced by the simple fact that you can do partial deployments. And if you look at some of the other talks in this conference, where people are talking about Docker and Kubernetes and things like that, part of the reason that these systems are emerging is that they let you control deployment in a much more fine-grained way, and that reduces your risk. The other reason that we use microservices is it's part of challenging some of the established norms in this industry, some of the established best practices. And by that I mean, sometimes in this industry, because it's a young industry, because we pretend that it's engineering, when it's really just emotion and gut feeling a lot of the time, we use things like agile processes and Scrum and Kanban and all these things as religion. And we promise ourselves and our managers that this will remove risk, and this will ensure that the project is going to be complete and delivered on time, and it will work in production. The problem is we're promising 0 risk, when that's exactly the wrong way to deal with these problems. So if you remember, I think it was 1986 when the Challenger shuttle exploded, and it exploded because they took off when it was too cold, and the rubber O-rings that sealed the rockets fractured because they were too brittle. And there's a famous video, if you look for a physicist called Richard Feynman, where he's in a one of these American congressional panels, and they're having a big argument about what the problem was. And he takes out some ice water and some of the rubber, and he puts it in the ice water, and then it shatters. The problem is, instead of doing the real science, instead of doing the real measurement, we're using pseudo measurements that don't actually help us. So we have to accept that there's no way to remove risk. What you can do is reduce it. You can reduce the risk that the project won't work. You can reduce the risk that it will fail in production. But there's another step. It's not enough to say, I've reduced risk. Great. Gold star. You've reduced risk. How much? And this is where our work goes from something that is young to something that is professional. It goes to something that makes a real difference in the world in a controlled way, is that we can measure how much we're reducing risk. So the way that we do it now with things like unit tests and quality assurance and code reviews and all that sort of stuff, they sort of work. I would certainly always use unit tests, of course. But the problem is they don't really solve the problem at a deep level. So we deployed a system in early February that had 600 unit tests. It wasn't a microservice system for various other reasons. It was a Node.js system. It was run by a guy who can do agile software project management really, really well. 600 unit tests. It went into production and it failed because there were production issues that had not been anticipated. So you can say, I have 600 passing unit tests, I have 90% coverage. These are measures, these are numbers, but they're not good numbers. They don't actually tell you by how much your risk has been reduced. The interesting thing about microservice-based systems is that they start to give you real measures of how much risk your system is exposing you to. On the other hand, one of the problems is that they also make your life a lot more difficult, because not only do you have the difficulty of measuring risk around and using unit tests and things like that that don't work very well, but now you also have a system that's got emergent properties. So the old techniques definitely don't work. You have to accept that you have to do things in a new way. You have to accept that the system is going to behave in ways that you can't anticipate. So it's much more important to measure the system in production, to measure the important behaviors of the system in production, rather than trying to decide whether the system works before you deploy it. And that's why your view of the world changes from one where you spend 3 months building something and then it goes live, to a world where after 1 week you have a live system as such. It might not be exposed to the public, but after 1 week you have a live system, and then everything else is modifications to that live system. Adding new microservices, modifying existing ones, removing redundant services. And you're measuring on a continuous basis to make sure that system is healthy. And every time you make a change, you're measuring what it does. In traditional monolithic architectures, this approach has been used by people like Facebook and GitHub, and because they're building monoliths, the way that they do it is something called feature flags. So you have an if statement that activates a new feature. It kind of works. The problem is it makes your code extremely messy. And these companies have accepted messier code because the output is lower risk in production. The nice thing about microservices is your code doesn't have to be messy anymore. Microservices are really small. Instead of having if statements and feature flags, an entire microservice is the feature, and you can turn it on and off by itself. It makes your life a lot easier because your code stays simple and clean. You move the complexity of that management onto things like Docker and Kubernetes, which are quite good at looking after that stuff. So I'm like to propose a new way of dealing with risk. And this is something that we've started doing in production and that we found works really well. So you have your normal best practices there in the middle. And you have this measurement idea of measuring a system in production. Deployments are things where you change small pieces and you measure the effects. And if you don't like the effects, you can roll back. And then there's the question of what to measure. And this is where formal methods come into play. So this is also about professionalizing software development, building the right mathematical models that can generate the right things to measure. So I'll just return to my initial example. If you're doing dynamic measurement, you could measure things like login rates. The problem with this picture is that the login rate by itself is a fragile measurement. It's different at lunchtime from midnight. So it's hard to control. So you have to find a way to describe it mathematically that's easier to measure. On the other side, you can use formal methods to start finding these better measures. So is anybody planning to learn a new programming language this year? Put up your hand. Okay, so Go. Who's going to learn Go? And let's say Swift. Okay, Swift. You're going to learn Swift. Good. It's a cool language. I'm going to suggest that you learn this language. Okay, so this language is called TLA+, and it's been around for about 17 years. And it was invented by a guy called Leslie Lamport, who is also the inventor of the Paxos algorithm and vector clocks and stuff like that. So this is a formal specification for a 12-hour clock. And if you look closely, it's actually fairly easy to follow. HR is a variable, the hour, and it can only ever be a number between 1 and 12. And then as the system advances step by step, I increment the hour. And if it's 12, I go back to 1. And it's a really, really simple but mathematical specification of a system. And this specification, I think, is really powerful because it doesn't have any boxes and arrows, right? This is a real description of a real system and how it works. You can measure this system. So this one is easy, right? This is obviously finite and complete. Amazon has used this language to verify DynamoDB and S3. So the problem that Amazon has with DynamoDB and S3 and some of the other systems is that data destruction bugs are really bad. They never want to destroy your data, right? They'd rather have a system that's not available than destroy data. So Amazon, for example, has a TLA+ specification of DynamoDB that extends to about 700 lines. Now, how do they use that to verify DynamoDB? If you try to run that, if you try to prove it, so if anybody who's actually used formal systems or studied them in university knows that the whole idea is that you prove that something is correct, except that that doesn't work in practice because the state space is infinite. But what you can do is you can apply the same techniques that you use to write chess-playing programs. A chess-playing program doesn't examine the entire state space of the game. It only examines down to a certain level. So, for example, Amazon took their description of DynamoDB and ran it down to 35 steps. Examined the state space across all these variables for 35 steps, and they found a data destruction bug. Now, you could examine the system to 70 steps or 140. What you get is a probabilistic measure of the correctness of the system. And that's where the real power comes in, because you can decide where your comfort level is around the probability that there's a bug. Not the guarantee, not zero risk, but you have a good measure of where your risk is. And the nice thing about TLA+ is that it's designed for describing distributed systems, which is ideal for microservices. Now, you don't actually need to learn this language to make use of most of these ideas, because the important thing about that clock, that 12-hour clock, is that there's an invariant. HR never goes outside of the numbers from 1 to 12. So you can take that idea that there are these invariants, there are these things that your system that should always be true about your system, and measure those. So here's an example. I have a microservice system. It's an e-commerce system. And I have a microservice that looks after the shopping cart. And I can send it add item messages when somebody adds an item. And I have another microservice which looks after sales tax. And whenever I add an item, the shopping cart microservice generates another message that says, calculate sales tax. There's a relationship and invariant between those two messages, between their flow rates. Whenever I get one, I should see the other. And it doesn't matter if it's midnight or lunchtime, the relationship, the ratio should always be 1. It's a dimensionless number. And instead of just measuring the number of sales tax messages per minute, I can measure the ratio of the two. And that means that if I deploy and break something, it doesn't matter if my deployment is in midnight or lunchtime, I still have a good measure of the health of my system. Okay, so like I said, learning TLA Plus is something that will take you 2 months. Finding invariants is hard if you don't have this formal description of your system. But you can cheat, because we already have patterns that we can use. So, for example, with the actor pattern, it's fairly obvious that if you have n actors, each of them should get 1/n of the messages. And you can start using these patterns to generate easy invariants. You don't even have to think about them. Or the subscriber pattern, where everybody should see a message. Or the chain, right, where each part of the chain should see the message. So people sometimes ask me, well, how do you actually, let's get practical. How do you actually measure the number of messages? Well, in reality, when you're writing your own microservices, you can send data points to something like InfluxDB. You can hook up New Relic. It's not actually that hard to do this. You don't need that much infrastructure. Tree is another example, right? So all the leaves ultimately should get a message. This way of thinking about the world turns the way that we work as software developers upside down. And the guy who introduced some of these ideas into Amazon, he wrote a paper, and in that paper he put it really, really well. He said, ask not what can go wrong, ask what must go right. Ask not what can go wrong, ask what must go right. All of those unit tests are checking to see that you haven't introduced errors into your system. But what you actually care about is that when somebody hits buy on the shopping cart, that the invoice is sent and the email is sent, the system actually works. So you start from the principle of saying, here is a formal, or perhaps a rough formal description of the system. Here's how that maps into the relationships between messages. And here's how those messages correspond to the reality that I want to see. And that's what I'm going to measure first. Afterwards, I can measure CPU levels and all that sort of stuff. But first, I have to ensure at all times my system is correct. And that lets me do partial deployments. That lets me do rapid innovation. That lets me get the most benefit out of microservices. So, for example, you do a partial deployment. You change some aspect of the login system. Each login generates an announcement message that says, this user is logged in. And let's say in this case, there should be 2 sub-messages. And I deploy a new version of the login system, and now my invariant goes down. And I know that I've broken something, and I know that I should roll back that login microservice. There are people out there, right, and I can say this because their chief architect has said it. Gilt Group are a luxury goods version of Groupon. And they were aggressively using microservices, so aggressive, in fact, that they don't mind breaking production. And they do things like every developer gets to deploy microservice anytime they like. And stuff breaks. Login goes down for 20 minutes. And if you search for Gilt Group microservices, you'll see some of their talks about this stuff where they freely admit that they keep breaking their own system because it's much more important to them to innovate rapidly. Now, that's okay. That works in a world where you're doing consumer internet stuff, and if you didn't get a deal, well, come back tomorrow. Most of us have to work in a different world where the software pretty much has to work properly all of the time. But we want to use this microservice concept to let us move faster. We can take this measurement approach, and it can allow us to do that by giving us a good measure of how much we're reducing risk. So, a couple of practical examples of how you can use this. The business rules of your system often break down into message flow relationships, just like the shopping cart example earlier, right? So if somebody buys something, there should be an invoice, there should be an email sent out. These are simple business rules, probably written down in a Word document somewhere. You can encode them by encoding the relationships between messages between microservices. Another interesting approach is learning from other industries. So if you are working on an oil platform in the North Sea, it's dangerous work. And over the years, to reduce accidents, the industry has come up with a number of standards. So if you're flying a crew on a helicopter out to an oil platform, the wind speed must be below a certain amount. The pilot can't have been flying for more than 10 hours. The helicopter must have been serviced within 4 weeks. All of these types of measures. And you can apply the same measures to your system to know when it's going to fail. But actually, you can get even more risk reduction if you combine the measures. So the oil industry has something called the rule of three, which is if any three of those measures are subcritical, and that means they haven't gone over the critical level, so technically it's okay to fly. But if any three of those measures are, let's say, within 90% of failure, that also means there's a problem. And you can use this in your own systems, because you can have different measures that may be approaching failure. And that tells you that today, maybe today, is not a good day to deploy a new version of a microservice. Maybe today you should be figuring out why your system is slowly going wrong. And again, this is about reducing risk, allowing you to do these partial deployments. So, to conclude, if you're going to use microservices, the system has to be measured in a different way. Microservices do introduce more complexity. They do introduce more risk. You go from a system where you can fully describe it, where you can draw an architecture diagram, to a system that's like the human body, that you can never fully understand. And over time, as you're running the system in production and different people build different microservices and deploy them all the time, the system becomes bigger than one person can understand. But what you can understand is what is meant to go right. What parts of the system are meant to work in certain ways. You can encode that in invariants, and the easiest invariants are defining the relationships between message flow rates. If you'd like to see some of these ideas in practice, so we have a Node.js framework, senecajs.org, that lets you build microservices. We've been experimenting with this measurement-based approach, and we're going to start open sourcing some of this stuff over the course of the year. And I'll let you see how we do some of this stuff in practice. And that is pretty much that. Thank you very much. And we have time for questions, I think, as well. So there's a timer, there's a 20-second timer on questions, and if you don't ask, I'm going to go get some beer. Okay. So the question is, what exactly are you measuring, and what sort of instrumentation do you have to put into microservices to measure the messages? So let's go back to my example, which is a shopping cart. So there's an add item message, and then there's another microservice which calculates sales tax. One way of measuring it is indeed to instrument the services. So go and buy a New Relic account, and then every time you see a message, it's a data point for New Relic. Another way is use a system like Kafka, where Kafka is the point at where you measure what message flow rates are going, and that means you don't have to pollute the code of your microservice with measurement code. Another way, and this is the way that we do it mostly in practice, is if you're writing microservices, you're following a particular architecture pattern, which suggests that you should have a set of utility code that helps you. So instead of writing your microservices where they're making direct HTTP connections to other microservices using a HTTP library, wrap that in an abstraction layer. And that abstraction layer is a good place to put instrumentation. The whole point of microservices is to make your code smaller and less complicated. And then where you actually store the data, in some ways message flow rates are relatively trivial because they're just time series. Ultimately, they're just number of messages per second or number of messages per minute. And you do need to do some aggregation and post-processing to get those ratios. That's why things like InfluxDB or New Relic work really well, because they do the aggregation for you. One of the points of this talk is that although I talk about some mathematical ideas, and some of them look kind of a little bit crazy, in some ways, on a practical level, this stuff is pretty easy. It's more having a mindset. It's more understanding that unit tests don't help you as much anymore.
In your example with login, like when the user is logged in, I need to notify your monitoring system that he is successfully logged, right? And this should be done asynchronously.
So yeah, it could be done asynchronously. So
No, it should be done asynchronously. Otherwise, it will delay.
yes. So the point is that when you're capturing this data, it has to be asynchronous. And in some ways, this instrumentation or data capture is quite tolerant of fuzziness. So because they're ratios, if some of the messages are dropping because things are under high load, it doesn't actually matter that much. It's still obvious that you've broken something. So the question is, how do you combine this microservice deployment approach and monitoring with more traditional ticketing systems and handling customer issues? So, like I said at the start, this is the start of an exploration. In some ways, we haven't seen a direct effect yet. And microservice architectures make that problem more difficult. So a customer ticket comes in saying, I've seen this problem occur in the system. And that problem might have been caused because 4 weeks ago you added 2 microservices, but you weren't measuring the right things. I think that's an open problem. But the trade-off is you get to move faster and you get to build more features. It's not something that has caused major blockages for us. And sometimes microservice systems are, in some ways, they're easy to kind of simulate. So if you look at some of the talks that Adrian Cockcroft has done, he used to be the chief architect of Netflix. He's written a simulation system in Go for simulating microservice architectures. So in some ways, what you would have to do there is go back and simulate the system as it was 4 weeks ago. But It's not something that has caused us huge issues in production. I'm sure it will. Okay, I'm going to say goodbye. Thank you very much.